Good afternoon, everyone. I would like to thank the organizer for giving me an opportunity to present my work here. So today I will talk about the construction of Maxfaces with infinitely many swallowtails and planar ends. Oh, sorry. So first in the preliminaries, we see some terms which are required to construct infinite genus Maxfaces, and we will see their singularities, and we'll see some example of singly periodic Maxfaces. So first, the Lorentz-Minkowski space is even 3 is a vector space R3 equipped with the bilinear form, which is defined by if U and V are vector of R3, then the bilinear form is defined like this, and we call it Lorentz metric. So a vector in Lorentz-Minkowski space is said to be space-like if V is 0, or with the bilinear form it is greater than 0, time-like if it is less than 0, and light-like if the vector is 0, not 0, but with the bilinear form it is 0. So in the last few lectures, we see minimal surfaces, which are zero mean curvature immersions in Euclidean space, and which are locally area minimizing surfaces. So we can also define zero mean curvature surfaces in Lorentz-Minkowski space, and which turns out to be locally area maximizing surface. So first we see what is max phase. So let X be a smooth map on a two-dimensional oriented manifold, and then the pair X with the manifold M, if it satisfies that the pullback metric on the pullback metric is positive definite for almost all P in M, mean curvature is 0 almost everywhere, and the differential map has full rank almost everywhere, that is except the major 0 set, then we call this pair as generalized maximal immersion. And if the pullback metric is positive definite for all P in M, then we say that the map is maximal immersion. So, and the points where the metric degenerate, we call them singular points. So the singular set is defined as all those point P in M where the map fails to be immersion. Okay, sorry. So a generalized maximal immersion is called max phase if the differential map has exactly rank 1 at all its singular point. So we see that the differential map has can be rank 1 or 0, but max phase are particular type of generalized maximal immersions which have particular type of singularities. So like minimal surfaces, we have Weierstrass-Ennepe representation for the maximal map or generalized maximal immersion. We are calling them maximal map here. So this is a method to construct a generalized maximal immersion. So what it says that let M be a Riemann surface, and G and omega be a pair of a meromorphic function and a holomorphic one form on M. Then, sorry. Then the map X from M to even 3 defined as real integral of these three components where Z0 is some fixed point gives a generalized maximal immersion if if P is a pole of G of order M, then it is a 0 of, then omega has 0 at P of order at least M. So we required this condition so that each component of this map is continuous, so integral is well defined, and mod of G is not equivalent to 1 on M, so that the map is regular. Otherwise it will be like one component, this will be 0 for, and for all closed loop in M, the period vanishes, that is the real integral of each component is 0. This condition requires so that the integral is independent of the path. So if the map X defined like this, if it satisfies these three conditions, then we say that the M with this map gives a generalized maximal immersion. Moreover, its converse is also true. So if we have any maximal map, then there exists a pair of meromorphic then there exists a pair G and omega, such that we can represent that map X as in equation 1. And moreover, this triplet, that M, G, and omega, we call that Weierstrass data for the maximal map. And we see that the pullback metric through this map is this. So we see that the metric degenerate at the points where the one form has 0, or the points where the mod of G is 1. So these are the singularities of the generalized maximal immersion. And we say that the map is max phase if we have the singularities where mod of G is 1. Okay. Now let us see some singularities. So cone-like and swallowtail singularity. So let X be a max phase and sigma naught be the set of singular points. Then a point P belong to sigma naught. We call it generalized cone-like singular point. If sigma naught is connected, compact, and its image is a single point. Moreover, if there is a neighborhood U of sigma naught such that its image is embedded, then we call it a cone-like singular point. So in terms of, so we can find the nature of a singular point in terms of the Weierstrass data. So if alpha is defined like this, so if alpha is at point P, if alpha is non-zero and imaginary part of alpha is identically 0, then we say that the point is cone-like singular point. Similarly, we have conditions for swallowtail in terms of the Weierstrass data. Let us see some examples. So let M be C minus 0, which we can see as sphere minus 2 punctures, and G be the meromorphic function and holomorphic one form. Then the equation 1 gives a max phase, and its singularity set is unit circle, which is compact. And we can see that its image by X is the origin, which is a single point. So every point of the singular set is cone-like singular point. Similarly, we have Lorentzian helicoid and Lorentzian NA per surface, which has folded singularity and swallowtail singularities. So these are the images of those surfaces. So this is the point where the unit circle maps to, and this is Lorentzian catenoid and NA per surfaces. So similarly, we can see more examples. So while constructing max phase, it is very natural to study either the map gives an embedded max phase or not, if it is complete or not. So here the embeddedness is defined in wider sense, means we cannot expect it to be embedded on the singularity set. So embeddedness here defined as that the surface is embedded except compact, leaving a compact set. And completeness is like if we have an infinite curve, then it has infinite length. For example, like a curve going near to punctures. And the type of ends they possess. So what is end? The end is the image of the neighborhood of a puncture through the map X. And we can see their genus and what type of singularity they have. So we see Lorentzian catenoid in the last slide, which is a Zener 0 surface, and it is complete, and it is embedded in wider sense, and it is two catenoid ends, which are, as we can see, it was a map from Riemann sphere minus 0 to infinity. So the neighborhood of those, image of the neighborhood of those punctures will give us catenoid ends. Then in 2006, Kim and Yang gave a family of complete generalized maximal surfaces. It's a one family, depends on G. So for G greater than equal to 2, and every maximal map has two ends. And we see that for G greater than equal to 2, it is not embedded, and they have increasing number of swallowtails. Then in 2024, Pardhan, Biswas, and Kumar established they give the existence of a new higher genus max phase, but here the end is NA per type end. Then in 2024, Chen, me, and Kumar and Mohanty, we give the existence of a family of complete embedded max phase. So in this case, so this is a one parameter family of max phases, which is complete, embedded, and which has arbitrary finite genus. and with arbitrary number of space-like ends. And the ends are either catenoidal or planar ends. So we use the node opening technique to construct these Maxfaces. So in the next section, I'm going to talk about uh, uh, I want to talk about a one parameter family of Maxfaces, which has infinite genus and with the infinite many planar ends, but all ends are planar. And moreover, each Maxface of this family is complete and embedded. So first, for that we need some input. We call it configuration. So what we need? So we want to construct a one parameter family that look like infinite horizontal space like planes, which are connected by small necks. So for convenience, let us label each horizontal space like plane by some integer k, and let nk be the let nk denotes the total number of necks which are connecting the kth and kth plus one space like planes. And to each neck, we associate a complex number, which will give the horizontal position of that neck. So in this configuration, we got, so in this input, we got a sequence of complex numbers where k is belongs to integer and I runs between the from I to nk, where nk is the number of necks in that layer. And we call a sequence of complex number and as a configuration. So we call this sequence of complex number as configuration, and we call it type of nk, where this sequence gives the number of necks connecting the two copies of horizontal space like planes. And let ck be the real number which correspond to the size of the neck in each level. And so for each neck uh, in the configuration, we define the forces which are exerted Fki, which are exerted on Pki by the other points. So Fki is defined like this, where this Pkj are the points which are in the same copy of complex plane, and these are the on the next, and these are in the preceding copy. And so we call configuration is balanced if for all k and for all I, these Fki is 0. And we call that this configuration as non-degenerate if the differential map of these Fki with respect to all Pki has full rank. So for the non-degeneracy condition, we see that we are assuming this Fki belongs to the sequence of set of bounded sequence. And we see that in some configuration, the non-degeneracy condition was not fulfilled. And we need non-degeneracy condition for the proof for the construction of these Maxfaces, because we want to use the implicit function theorem where we need the differential of these Fki. So we give some translation to Pki and defined as Uki and Lki. So in this way, we get a new sequence of complex number like this. And we can see by that the UK1 are 0 for all k. And so now we call this new sequence as our configuration. And we can define this translation because our forces are independent of the translation. So if we translate and scaling, the Fki term, Fk forces will remain same. So now we define Fki in terms of these new parameters. So by assuming all these things, we got a family of Maxfaces. What it says that consider a balanced and non-degenerate configuration U, which is of type Nk, and further assume that the sequence Nk is bounded. Here, we can also explore for the when this sequence is unbounded, but since we are putting pki's in the L infinity, we are taking pki as the sequence of as a bounded sequence, so we need this condition. Similarly, the sequence U takes the finite number of values because our pki sequence is finite value. And for all k belongs to Z, this condition satisfy. We require this condition for the because this will give that the Gauss map we create has all of order 2 at the punctures. So that will give the for planar ends. So then if all these conditions fulfill, then there exists a one parameter family, MT, where T is a real parameter of complete embedded Maxfaces with infinite many planar ends and with infinite genus. Furthermore, each surface MT is periodic or quasi-periodic if and only if the configuration is periodic and quasi. For example, we say the configuration is periodic if there exists a positive integer t such that these nk plus t and they all kind of repeat with the t. They all are periodic. So we will solve this, we will prove this theorem using the Weierstrass-Ennepe representation. So for that, we need a Riemann surface, a Gauss map, or say a meromorphic function, or and a holomorphic differential which satisfies some conditions. So first we construct the Riemann surface. So for that, we construct a Riemann surface by opening the nodes. It is a method used by Martin Trejet and Morabito in constructing a family of minimal surfaces. So to each horizontal space-like plane K, we associated a complex plane C, which can be seen as Riemann sphere with one puncture. And the copies of C as well as their punctures we index by some K just for the convenience. And to each neck, we associate a point AKI belongs to the CK layer, and corresponding to this AKI, we assign a point BKI, which belongs to the CK plus 1 copy. So I don't know. So we can take for the three layers. So if I draw it like this, just complex plane with one puncture, and let us assume that K is 3 for time being. So what is saying that so it is K equal to 0, K equal to 1, and K equal to 2. So we are taking AKI. So say let us say that N0 is 1. That is the neck connecting this and this. We have only one neck which is connecting. And let us say N1 is 2. That is there are two necks, and N2 is 2 which are connected. So let A naught 1 be point which belongs to the copy C naught, and corresponding to this point we have B01. Similarly, we have A11, A12, and B11. Okay. And so what it says first, so if we just identify these points, then we get a Riemann surface with nodes, and we call it noded Riemann surface, and we denote it by sigma node. So now for each copy of complex plane, we define a meromorphic function gk, where these alpha ki and beta k minus I, they are all complex number, and we see that this is a meromorphic function which has pole at aki and bki. We see why we are defining this function. So now we see that now we say that any sequence of complex number is finitely value if the set is finite. We see why we need this finite hypothesis. And so for each this sequence, for example, the sequence of AKI and BKI and alpha KI and beta KI, we defined the central values for each parameter such that the parameters AKI and all those parameter varies in a neighborhood of these central values. So now we choose an epsilon sufficiently small. So we can choose this epsilon because of the finite hypothesis, which says that the sequence is finitely value. Because here we have like infinite sequence of AKI and BKI. So we can choose epsilon sufficiently small, which is independent of KI by taking their minimum of around the neighborhood. And we defined a chart around the, we define a chart VKI around the point AKI and WKI around the point bki by, this is 1 by gk. So here it is 1 by g and it is 1 by g1. So this will go to some disk of say epsilon radius around 0, where these, so how we are defining this map? By the meromorphic functions we define above as the local So now for some t greater than 0 and less than epsilon, we remove the disks uh, of radius t square by epsilon. So similarly, since they are diffeomorphism, we can remove a neighborhood from here. And then, so we get to annular region. So we identify the points of these annular region by identification that Vki of z into Wki of z dash is equal to t square. And thus we get a Riemann surface. Thus we get next around each point. And so we get a Riemann surface sigma t, where with the change of t, we get a new Riemann surface. Okay. Sorry. So also we defined the Gauss map with the help of this meromorphic function. And we defined the height differential or holomorphic form. Okay, we defined the holomorphic form. And since by prescribing the period of by prescribing the period around the canonical homology basis. So in 2013, Trejet gave a theory of holomorphic differential on a non-compact Riemann surface obtained by opening infinitely many nodes. So we know that there are some results for which that if we have a compact Riemann surface minus puncture, so we can define a meromorphic, which give the existence of a meromorphic differential form. So here he give the existence of the holomorphic differential form on sigma t, which is non-compact and which is obtained by opening infinitely many nodes, and which satisfies some condition that in each layer, for example, if we have a period here and or some period defined around this curve, so their sum should be equal to the sum of the periods around these points. And moreover, as t tends to 0, we say that omega converges uniformly on a compact set. So here we do not have explicit expression of the holomorphic differential. We say that there exists some holomorphic differential, and as t tends to 0, the holomorphic differential looks like this. So this is the canonical homology basis for these Riemann surfaces. It contains the curves which are in the neck, like which are in the annular region this. So a curve here is homologous to the curve here with opposite orientation. And the other curves are which start from one neck, goes to this neck. Since this neck and this neck are identified, so from here to we can reach here, and then we come to the first neck. And since this neck is this annular region is identified to this annular region, so we get a closed curve like this. So this is the canonical homology basis. So in this way, we get the Riemann surface and the Gauss map and holomorphic differential form. So by solving the period problem, we get a family of Maxfaces. And we see the singularity, we see in the definition, the singularity set of these Maxfaces are given by the points where mod of G is 1. So from the definition of the Gauss map, so we see that from the definition, which was defined as like T of GKZ or for K odd or something. So we know GKZ we can write as T of VK comma I of Z. And so its mod will be, so its mod is equal to 1 when VKI of Z is equal to T. So the only singular points we have are in the necks. And So as we see that we have some criteria to check the nature of singularity in terms of the Weierstrass data. So in the paper of for finite genus, we introduce a new function called a t theta, which is defined like this. And by solving, since we don't have explicit expression of this differential form, so we cannot explicitly give that what that singular point will be, what the nature of that singular point will be. So after solving this, um, we get this expression which is independent of t, and which we can find out with the help of just the configuration and omega k. And moreover, we see that when the r is 1, if rk1 of theta is non-zero, so that we have cuspidal edge, and if it is 0, then we have swallowtail singularity at those points. So let us see one example, which is height 2. uh, a height 2 family. So a configuration is given by these points. Okay, so here we have, like here, k is 3. So first two layer are connected by one neck, second and third are connected by n necks, and the third and fourth layer is connected by one neck. So we can get this configuration with the help of the balanced and non-degenerate conditions. And we see that this configuration is balanced and non-degenerate. Moreover, we see that this configuration is unique up to the permutation group Sn. So if we see these points, so and so they are moreover, this configuration is unique up to the permutation group on this P1J point. And when n is 2, the configuration correspond to the Lorentzian V-type surface. And we can construct an infinite genus surface by concatenating these finite configurations, which are balanced and non-degenerate. So if we just repeat this configuration, then we get a infinite singly periodic configuration with alternating layers of n necks and one neck. So this is the sequence for the infinite genus surface, where we have one neck, n neck, and one neck and there. And its period is 2. And the configuration for the infinite genus Maxface is this. Okay. And moreover, we see from the expression of rki theta, we see that for even k, rk1 of 1 theta is identically 0, and when k is odd, we get this expression of this. So we see that in even layers we have this RKI is identically 0, and their singular curve might degenerate to cone point. On the contrary, in the odd layers we have except on isolated points it is non-zero. So these isolated points will be swallowtails, and the others are cuspidal edge. So therefore we see that every neck in the odd layer produce 4 swallowtails. So in this way, so we get a surface of infinite genus with infinite many swallowtails. And so this is the another example, which is of height 3. And we see that this configuration is also unique up to the cycle permutation in the second and third layers. And this is the expression corresponding to each neck. And moreover, we see that in this example, each neck has swallowtails. And so from the proposition that the configuration has vertical reflection plane that cuts through the neck of interest. So here we have YZ plane vertical reflection, YZ plane reflection. So the singularity around the neck that is fixed by the reflection is non-cuspidal. So in this we see that uh, the layers with one neck have non-cuspidal edge singularity. Moreover, here each neck has 4 swallowtails. So this is a Maxface which has again infinitely many swallowtails. So we also discuss. So this was done for when our t was not changing for a fixed t. We also examine how the behavior of singularity is changing with the change of the parameter t. That is, if we have a cuspidal edge for some max phase xt node, then it says that there exists a small neighborhood around the t equal to 0, such that the same point, that theta node, serves as cuspidal edge for the max phases for non-zero t in this neighborhood. And also we see that if we have a swallowtail, then there exists again a neighborhood around t equal to 0, such that this theta naught either remains swallowtail or change to either a cuspidal edge or a cone-like point. So these are the references.
Thank you for that wonderful talk. Are there any questions from the audience? Maybe I start with one. So in the theorem that you mentioned from 2024, how do you show embeddedness?
Actually, we show embeddedness by Schiffman theorem.
Okay. Could you say a little bit more, maybe?
So we show embeddedness. We say, as I said, that embeddedness we define in the wider sense that accept a compact set which contains the singularity, or which removes the singularities.
Okay. So wait.
So when you cut the each neck through a horizontal plane, so it will give a closed convex curve. And so by the Schiffman theorem, which says that it is foliated by, if we have two closed convex curve in the parallel planes, then it is foliated by the closed convex curve.
Okay.